Hello, everyone, and welcome to the Distinguished Speaker Series put together by WinCom and the Sociedad Matemática Mexicana. So thank you again, everyone, for your participation in this series. Thank you to the SMM for your support and your organization in creating this wonderful series. This is a 10-week series, so we start today, March 23rd, and we'll go straight through to May 25th, the end of our year. And we have some wonderful speakers to host, some wonderful women in combinatorics from various universities in Mexico or tied and affiliated in some way to the SMM. And we're so thankful for the inclusion in this project and all of the help and support and organization that we've gotten from the SMM. So thank you again. It is my pleasure to introduce our first speaker of this series, Dr. Silvia Fernandez. Silvia comes to us today from California, and I'm very much looking forward to this talk. This is a great start to our series, and thank you again. Take it away as soon as you're ready, Silvia.
All right, so let me share again. All right, so thank you, Erin. Thank you, everyone, for being here. And thank you, especially to the Women in Combinatorics group and to the Sociedad Matemática Mexicana for putting this together. I really would like to encourage everyone to not miss any of the future talks in the series. Some of my favorite colleagues are talking, so please come back. Anyways, the title of my talk is a little general, very general, but the reason why I did this is because I want to emphasize the tool that I'm using and I've been using in my research for a long time now, rather than the results. Although I really want to share these new results that my student and I have been getting lately. So about half of the talk, I'll tell you more about the tool and different ways that you can use it. And then we'll get into more recent results. So let's go right into the tool. In this talk, I only care about finite sets of points, at least at the beginning, finite sets of points in the plane. And so my tool is called circular sequences. So any set of points in the plane can be assigned something that's called a circular sequence, which is nothing else but a sequence of permutations of the points. So we're listing the points in some order. So here I have a set of 8 points. Imagine that they don't have labels yet. So it's just the points. We're gonna get the labels after. So I have them there, but originally you only have the points. Take a circle that contains all of the points and take a tangent line in any direction. I usually start with this horizontal tangent at the bottom. And then I take all the projections of the points to the line. Those projections will give me an order along the line left to right. And that's how I get the tags, 1 through 8 in this case. And then my points inherit those tags. And they're gonna keep those tags for the entire process. So it doesn't really matter the size of the circle. We don't even need a circle, but it visually helps. And then we're gonna start rotating that tangent line around the circle and keeping the projections of the points. And so as we move, those projections, those dashed lines that you see there are gonna start overlapping. When they overlap, there's gonna be a switch in the order of the points along the tangent, and I'm gonna record that order. So here. So that's my beginning stage. And then I start rotating. And as you can see, the lines for 7 and for 8 are getting very close. Same for 4 and 5. And as I keep going, they eventually overlap. So 7 and 8 project to the same point right now. And right after, they change order. You see, I had a completely increasing order. So I had 7 before 8. And now right here, I have 8 before 7. So I'm gonna record that order in my circular sequence. I started with 1 through 8, and then here I had a switch with 8 and 7, and I just keep going like that. So you're gonna see this same sequence that I have on the right, this finished sequence is gonna be appearing here as soon as the changes happen. So the next one is 5, 4, and then 5, 3, 4, 3, etc. And so as you rotate, you're going to have all those changes. Those switches correspond to connecting lines of the points. For example, right there, when 4 and 6 overlap, that's just a connecting line for 4 and 6 being perpendicular at the time that is perpendicular to my tangent. And that's what I'm recording here. So 4, 6 is someplace over here, and I'm switching that. So at the end, after half a turn, so after 180 degrees, if you imagine that your line is actually directed, so it was directed left to right here, now right to left, the order of my points is actually 8, 7, 6, 5, 4, 3, 2, 1. But it's actually the same order, the exact reverse order of how we started. So right here, we started with 1 through 8. We finished with 8 through 1. We could keep going around, and what's going to happen is that because here 8 and 7 switch right away, in my next step, if I keep rotating, 8 and 7 will switch here. And it's just going to be the same sequence that I have, just the symmetric. I could also go backwards. I can go clockwise instead of counterclockwise, and my sequence will continue this way. So this is really a doubly infinite series of permutations of the points 1 through 8, or my labels 1 through 8, in which, in this, that I call a half period, because it contains all of the information. A half period because I will have the symmetric there to have a full period to get back to 1 through 8. So, but the half period contains all of the information. And that's all I need to keep a lot of the combinatorial information of my set of points. So this circular sequence is associated to this set of points, but I want to see how I can construct, or if I can construct other sequences like this without having the set of points. Because you see, even if I didn't have the set of points here, I could have said, okay, let's just start with the 1 through 8, switch 8, 7, and then switch 5, 4, and then switch 5, 3, and so on, without having it here in front of me. So if I do that, if I were to do that, the question will be, okay, now I have something that looks like a circular sequence. Can I find the set of points that goes with it? And the answer is not in general, but we'll get to that. What I want is to see what are the properties that this sequence satisfies. And essentially, because it comes from a set of points, I will have switches only when, again, the two lines, let's see here, for example, 5 and 8, two projections overlap. That's a connecting line. So that's what I'm recording there. So I'm recording all, because this set is in general position, I have at most 2 projections overlapping at a time. And that's why I only have switches of 2 points here at a time. And therefore, when I have a set in general position, I'm going to have that every set of points switches exactly once. Any pair of points switches exactly once. And so here I have 8 choose 2 rows. I will look at 1 through 8 as my heading, and then the switches are recorded from here, 1, 2, 3, and so on. So I have 8 choose 2. The points don't need to be in general position. So I'll give you an extreme example where the points are all in a line. So how does that look like? So what if I have all my points are collinear? This example. So I do the same, I project everything into my tangent line, I have my tags, then what happens? They start moving, all the lines overlap, and then they get apart, right? But they overlap only once, and everything switches. See, if I go back here at the time that the switch happens, I have 1 through 8 all throughout, and when they overlap, they all switch, and then afterwards I have 8 through 1, completely decreasing order. So this is my half period. That's super easy. So this configuration is what I call the trivial configuration, and I have to exclude it from most of the problems that I'm interested in because it doesn't go with the pattern. But you see, that's our first example. What else can happen? Besides collinear points that correspond to switches of more than 2 points at a time, we can have parallel lines. So parallel lines will also correspond to switches that happen in the same permutation. So for example, here I have all these points align, they're collinear. And this set is actually centrally symmetric, so that when I look at 6 and 3, they kind of behave the same way. And so these lines, 6, 1 is parallel to 3, 8, 2, 6 is parallel to 3, 7, 6, 4 is parallel to 3, 5, and so on. So these sets of parallel lines is what I'm seeing in my allowable sequence, in my circular sequence right here. So 3, 2, 3, 2, I haven't marked it. So 3, 2 right here is parallel to 7, 6, this one right here. And they're happening at exactly the same permutation right there. So parallel lines also correspond to switches that happen at the same permutation. So let me, oops. So let me show you how this looks like. So this is probably very quick, but you can see there, I have an alignment of 3, 2, 1, 6, 7. Let me get to this line. So this line corresponds to this switch of several points. All the others are parallel lines. For example, let me get to one. Here, 6, 1 and 8, 3 are parallel, and they're switching. So it's 8, 3 and 6, 1. And then this one is another special one, 6, 3, switching with each other. You see right there, that would be the switch right there. And the fact that my set is centrally symmetric, I can also see it here. You see this set has a center right there. And for every point on one side, I have the symmetric on the other about that point. And so that symmetry I can also see here along this line. See? Along symmetry about that vertical line in my allowable sequence, not the tags, but whatever is happening, the switches. So these are circular sequences. This is how I obtain them. So let's say what a sequence like this needs to satisfy in order to have the possibility of coming from a set of points. So this is an abstraction of those circular sequences. They are called allowable sequences. And I think I said it already like 2 or 3 times because it's in my mind. So when my sequence comes from a set of points, I call it a circular sequence. But in general, the abstraction is an allowable sequence. And these are the rules that you need to follow. So essentially, you don't have to read them all. I'll give you an example. I start, let's say, with n equals 6. That's equivalent to having 6 points. So I start my first permutation. I'm creating a sequence of permutations of the elements 1 through 6. And the rule, so that's just kind of the beginning right here. You start with 1 through n. And then this one over here tells you that you need to essentially switch everything in a half period. So my goal right now is to get to 6, 5, 4, 3, 2, 1 by making switches of consecutive numbers of substrings, reversals of substrings that are in increasing order. So for example, here I could start with the 4, 3, 2, 1 reversing and the 6, 5. So 5, 6 reverses to 6, 5. It needs to be an increasing substring of consecutive elements or elements in consecutive positions. And so for my next step, because I can only, every pair of elements switches at most once before I get to, exactly once actually, before I get to the reverse 6, 5, 4, 3, 2, 1. I cannot switch for 4 with 3 or 4 or 3 with 2 or 2 with 1. So the only possibility that I have here is 6, 1. That's the only possibility that I have in this particular case. Everything else remains the same. They 4 already switched with 3, with 2, with 1 in that first move right here. So they cannot switch among each other until after we finish the half period. And then you can just keep going. Like here, I can switch 6, 2, and 6 and 2 and 5 and 1. I don't need to switch them at the same time, but I could if I wanted to. You know, I'm just constructing an arbitrary one. So it doesn't need to be greedy. I know that don't need to do everything that could be done, but you know, just to finish it earlier, I'm gonna do as much as I can in each step. So I can do 6, 4 here, 6, 3 here. And as you can see, 2 and 1, I cannot switch because they're already in decreasing order. And as you can see, sometimes I don't even write the elements that are not moving. And here my only other choice is 5, 4, and I'm back to the 6, 5, 3, 2, 1. So those are essentially the rules for creating what is called an allowable sequence. Now, does this come from a set of points? This one does, because everything with less than 9 points does. But after that, it's actually a very difficult question. So those configurations those allowable sequences that come from sets of points are called stretchable. And the reason why they're called that is because these sequences can not necessarily be or be associated to sets of points, but they could actually to generalized configurations of points where you can think of those as, give me 1 second, let me close this. You can think of those as sets of points, but the connecting lines are not straight lines. They could be pseudo lines. So look, this is really like the different rules where you can play. So these are configuration of points. These are generalized configurations of points. So one way to think about them is when you have a configuration of points, it comes with its connecting lines, right? All the connecting lines. In a generalized configuration of points, you can think of it as having some family of pseudo lines associated with it. So they don't need to be straight, but they need to be a family of pseudo lines. So it is known that every allowable sequence corresponds to a generalized configuration of points, but not necessarily to a configuration of points. So from all this diagram, and then I have duality. I have line arrangements, subline arrangements, and other things. But from this diagram, what I want you to keep in mind is that there are more allowable sequences than circular sequences. So any problem combinatorial in nature that we can think of for sets of points, we can possibly extend to allowable sequences, to generalized configurations of points. And so that's the key idea in this talk. Like, I want to tell you how I use it, but I wish, if you ever think that you might use it, like, does it apply to you? Will it be helpful? How would you use it? So here are some examples of problems where you can and where you cannot use them. So here, we talk about connecting lines. So you have your set of points. Let me zoom in a little bit more here. So you have your set of points and it comes with its connecting lines. So anything related to connected lines, it's actually there in the allowable sequence, in the circular sequence, because those are just the switches that I was highlighting. Those are my connecting lines. Ordinary lines are lines that pass through exactly 2 points. Exactly 2 points. So there is this classic problem, Sylvester's problem, that asks if it's always true, except for the trivial case where all the points are collinear, if it's always true that any set of points contains an ordinary line, so a connecting line that passes through exactly 2 points. And if you haven't thought about it, I recommend you to try it. It's a puzzle, and it's been a really hard puzzle for some people, but now there are hundreds of proofs. One of those proofs actually uses allowable sequences, and it's actually very a very easy proof. So that's any type of problems relating connecting lines. For example, the direct Moskine conjecture that says that not only there is one ordinary line, but there are at least n/2 ordinary lines for endpoints. You could try it using allowable sequences, and I work on it, and we have some partial results. But in 2012, Tao and Green actually proved that conjecture. That's a very big deal. They proved this conjecture, but only for n large enough. Not that I no complaints, but this n is very, very large. And the proof is this elliptic curves. It's a very difficult proof. So I'm wondering if, maybe this technique, maybe using allowable sequences might help, for either finding an easier proof. Not that, these two people, I have nothing to recommend to them, but I'm saying that maybe there is something that can be done, or to take care of this n large enough to take care of the small cases. And there are more problems. If you heard about the orchard problem, that's also related to connecting lines. So you can also approach any of those problems using allowable sequences. More than that, you can extend it to the world of allowable sequences, not only for sets of points, but maybe you can say something else for that larger world. Two other famous problems, maximum number of unit distance. This is called the unit distance problem, or the distinct distance problem. These two problems are by Erdős, and I think he proposed them in 1946, in the 40s. This you shouldn't try, because this involves the metric, and we lose the metric when we change to circular sequences. So you shouldn't try those. Anything that involves the metric, just think about it. The allowable sequence of a perfect square, so the vertices of a perfect square, is exactly the same as for any convex quadrilateral. So anything that, well, not exactly the same, because here I have parallelism, but let me backtrack. Not the same, because here I have parallel lines, but essentially any convex quadrilateral will have essentially the same allowable sequence. So no metric. Oops, sorry. The minimum number of directions. These are the slopes of the lines, the connecting lines. That's what I'm interested in today. So that's where I'm going to give you a little bit more. This is a perfect problem. This is the one problem that has completely been solved using allowable sequences. So most of the other problems that I have included here, like problems about, k edges. These are just connecting lines that separate k points from the rest. So k from n-2 minus k other points, because I'm using 2 points there. So if you want to maximize the number of 2 edges, those are the connecting lines that separate 2 points from the others, that all of those problems are open. Maximum number of halving lines is super famous, to essentially have n/2, actually I should say n-. Halving lines means that it's a connecting line that separates the set in almost half. So it's actually n-2 because of the 2 points that I'm using. And if any thought, I have to be a little bit more careful. But if maximizing the number of halving lines, that's something that you can approach using allowable sequences, and we have. And actually, we have results. And then crossings, the crossing number problem. That's my favorite. I usually talk about crossings, but not today. So I'll go to the directions problem. And if I have time, I can tell you more about this. But these are just examples of problems that you can try. Convex sets. Oops, why is this moving? Convex sets. Let me go back. I don't know. Convex sets, like the happy ending problem. you could possibly approach using these. I'll show you something. Let me go to another here, so that you know you can actually see convex sets in allowable sequences. This is a set in convex position, and here I have like color coded my switches. So this is in general position. So I'm going to have exactly, I choose two transpositions here. The red ones right there are the ones that happen in the middle. These are the halving lines. So if you want to count halving lines, if you want to maximize halving lines, what you want is to have as many transpositions as possible here happening in the center. If you want to maximize zero edges, those are the green ones. And those actually are the sides of my polygon. 1, 2, I have it here, 2, 3, 3, 5, and in order, 5, 7, 7, 8. And remember that I have the double, the periodicity. So the 8, 6 will appear after here. So 8, 6, 6, 4, and 4, 1. And then back to 1. So here's my convex polygon. So I can see convex sets here. If I wanted to see a subset that's a convex set, the sub-allowable sequence needs to satisfy that all the points get to the end. You see, this is the most left point at some point in my allowable sequence. So you see, for example, if I stop right there, 3 is my leftmost point, and therefore is in my convex hull. Any point in the convex hull needs to be in this position, first or last position at some point. So I can see convex sets. So any problem about convex sets can be tried using this. Okay, so let me tell you what's the last thing. I've used allowable sequences for many, many things. All of the problems that I mentioned, I've done something here or there. The latest is directions. So let me tell you the details of that problem. So this is the directions or slopes problem. The goal is an optimization problem. So the goal is to find the minimum number of directions. These are the slopes of my connecting lines, determined by a non-trivial, so not all the points are collinear, set of endpoints in the plane. Now, let's see. So if I have n choose 2 pairs of points in my set, right? So I could potentially have all of them being different lines and maybe all with different directions, just like super, super, super general position, not parallel lines, not collinear points, not anything. That will give me n choose 2 directions. So asking for the maximum is not interesting, but it gives me an idea of what I need. If I need the minimum, I want to have as many collinear points as possible, but I cannot have them all because that's a trivial case. So not all, but I want to have many collinear points and I want to have many parallel lines because those also give me the same direction, right? So sets with many collinear points or many parallel lines. Those will be, in principle, the ones that minimize this number. Well, in the 70s, Scott conjectured that this is the exact minimum. 2 fluorophane over 2, which is essentially n, right? N when n is even, n minus 1 directions when n is odd. And he had constructions, several constructions that achieve this value. So that's the reason for the conjecture. And then in the 80s, after Goodman and Pollack came up with allowable sequences, remember, this was conjecture in the 70s. In the 80s, Goodman and Pollack defined allowable sequences, and then Ungar in 82, in the early 80s. So Ungar in 82, almost right after, proved this conjecture using allowable sequences. His paper is like 4 or 5 pages long. And it's a beautiful paper. Well, a beautiful idea. I really like it. If you have a chance, it's a paper I would recommend you to read if you're interested in allowable sequences. And it's a full proof. It settles the problem. So after his proof, the focus changed to the classification of optimal sets. So which are all the sets, either an even number of points with exactly n directions, or an odd n number of points with exactly n minus 1 directions, which are all. That problem is still open, and that's what I've been trying. So that problem is open, but there are some conjectures. So I'll show you some of the configurations that achieve that number and how everything looks in the allowable sequence. So the regular polygon is one of those sets that regular polygon with an even number of sides. So it's n points, n directions. So in this case, my n is equal to 16 points. It has 16 directions. And I color coded some of this is the allowable sequence. You can see I have tons of parallel lines. Essentially, you can do this greedy. You see, I start with, the labeling of my points is a little different because my set is centrally symmetric. A regular polygon is centrally symmetric. And so what I'm doing is I am labeling, for example, 8 and 8 bar, the 2 points that are centrally symmetric. And so here I have my center. My center in this allowable sequence is not part of my set, but if I wanted to include it, it will be number 9. You know, when I project, it will be number 9, and it will be here in the middle. It will be like right here. Let's see, yeah, that would be number 9. It wouldn't move. Every time that there is a switch, like for example, here 7 bar 7 and 9 will switch. Like 8, let's do here 8 bar and 9 will switch. It will be this line right here. So anyway, so I've talked about central symmetry, how it looks in the allowable sequence. Now I have a lot of parallel lines. I have no triples, collinear triples, but I have a lot of parallel lines. And so here, these are the ones that correspond to diagonals parallel to a side. So these red ones right here, and then all the diagonals that are parallel. And then the light green, I don't know if you can see it, but the light green right here are the ones that are, these ones right here. The ones that are kind of skipping this vertex. And then I have the 1, 4, 3, 6, 5, 8, and so on. So in that direction, I'm using all of the points. It's almost a matching of my set of points, except for the 2 and the 2 bar. And the red ones, which was my first permutation, is a matching of my points. So that's what I have here in my allowable sequence. So this one is tons of parallel lines. Another example is the bipencil that I showed you earlier. That one has several parallel lines, but there's still many collinear points. That one has several collinear points. You see the bipencil is another one of those, another direction critical configuration. Now this one has many collinear points and some parallel ones. You see here I have some parallel lines, the blue ones, and then I have also lots of collinear points. And you can see here, in this one I had 8 points, and here I have 1, 2, 3, 4, 5, 6, 7, 8 directions. So the length of the half period is the number of directions. So what I want is to forget about the sets of points. My problem becomes the way that I was creating by hand that allowable sequence is a purely combinatorial problem, no geometry whatsoever. I want to know which allowable sequences, let's say with 8 points, which allowable sequences can be, or in which way I can reverse 1 through 8 to 8 through 1 in exactly 8 steps. That's what I want. Those will be the direction critical configurations. Here's another example. Give me 1 second, because this is bothering me. Okay, so here's another example. This is called the bicolumnar array. This is just a set of equidistant collinear points and another one, a parallel line. And you can see how the allowable sequence looks like. You see, again, a combination of some collinear points. So this time I have half of the points are collinear here, half of the other half are collinear there. So those are these black lines. And then I have, this is the only switch that I can do right away. You see, that's the issue, that every time that I have a lot of collinear points, then that kind of prevents me from having other big chains here. That's the idea that Ungar uses in his proof. And so I have to kind of start with the transposition 2, 3, and here I have a lot of parallel lines as well. And then I have this one. This is called a Tri Columnar Array. This you can actually, I have the definition, the full definition here. It is again like equidistant points, so like an arithmetic progression here, and in 3 parallel lines. So I could actually add some more points here. I could add some more points here, and it will still just keeping the central symmetry, and it will still work. Anyways, so this is a Tri Columnar Array, and this is how the allowable sequence looks like. Again, here I have a lot of collinear points, which is this line right there. And I have this other one. This is an exponential cross. It's called, well, it's a cross, but it's called an exponential cross because this is a geometric sequence. This is a geometric sequence here. So I have a certain distance lambda, and here I have lambda to 0, lambda to the first, lambda squared, lambda cube, and so on. So this is a geometric sequence, and there are 4 copies of it there. And so you can almost see all of these like diamond shape regions here correspond to all these switches, all those switches, one on each side. And then the ones that I left in black are all those switches and all these switches. Anyways, the reason why I'm telling you about these families of configurations is because when you're looking at here, at the classification problem, so I want the direction critical configurations. Those are the families that are conjectured to be the only ones. So just a note here that many times direction, what to me is direction critical for any event, because that's the best that you can do in directions. It's called near critical, just because you cannot achieve the n-1, but you can't, so the best that you can do in that case is n, but that's sometimes called near critical. So in the 80s, Jamieson and Hill, they came up with, Jamieson came up with this conjecture, but they came up with lots of sporadic configurations, direction critical configurations. Many of those were found by computer, but Jamieson conjectured that essentially the families that I show you are all the ones that are direction critical, meaning for the odd case. So a center even regular polygon, so like a 16-sided polygon that I showed you with the center, because here I'm just interested in n of, or a centrally symmetric bipencil that I also showed you, or an exponential cross. That's the one that I just showed you with the, the cross with a copy of a geometric progression in each of the wings, and a Tri Columnar Array, which is 3 arithmetic progressions in 3 copies of an arithmetic projection in 3 parallel lines. Other than that, they have a catalog. Well, this was done in the 80s, 102 sporadic configurations, and I think that there are 2 more that came up later. So over 100, but very close to 100 sporadic configurations. And what is interesting is that only 4 of them are not centrally symmetric. These are the 4. From everything that's known for the odd case, remember, these are the only ones that are not centrally symmetric. There might be others, but it is conjectured that after, for n large enough, any direction critical configuration falls in here. There are some other results like this one right here. If you have a new critical configuration, so an even number of points in general position, then essentially the regular polygon, the vertices of the regular polygon, is the only direction critical configuration. So any other is affinely equivalent to it. You know, affine transformations preserve the number of directions, therefore there's going to be more, but all of them are affinely equivalent to the regular polygon. So there are some other results like that. But so what we decided to do, because it's believed that most of the configurations, critical configurations, are centrally symmetric, we decided to focus on centrally symmetric configurations and kind of start from the point, you know, something a little more than general position. So this is what we looked into. I need to give you 3 definitions. Well, central symmetry, you know what it is. And I went through how it looks. My plan was to go and look at how it looks like in the allowable sequences. But then non-central general position, what that means is an extension of general position for centrally symmetric sets. So I am allowing to have some collinear triples, but they need to be connecting lines that pass through the center. So for example, this set that I have here is in general position. It is okay to add points, for example, here. It's okay to add points there because that's a connecting line that passes through the center. So I'm allowing that collinearity, but it's not okay to, for example, have a point right there because this line doesn't pass through the center. That's non-central general position. Okay, so, and then the central degree and the central signature, which is, I'm defining them here for centrally symmetric sets, but there is a more general definition for that. So for example, I added those few points there. So let me add just a few others. Let's say that I add these ones. The rest was in general position. And yeah, let's say that I just do that. So I'm gonna count how many points on each line of the center, well, on each side of the center, there are in each central connecting line, the ones that pass through the center. So here I have 2 points on that side. In the others where I didn't add anything, I have one on that side of the which side of the center. Here I have 3. Here I have 1. Here I have 1. Here I have 1. And this is starting over. Let's see that's the same line as for the 2. So my central signature will be 2, 1, 1, 1, 3, 1, 1, 1, and it's cyclic. So the order is important. The cyclic order is important, but it doesn't matter where I start. And the degree is just the number of lines passing through the center, which are actually halving lines. All right. So here are the results. So we have the full classification under these properties. So we look at all centrally symmetric configurations in non-central general position. And we first look at the problem for allowable sequences, right? And surprisingly, we came up with this, we proved this result. Surprisingly, for any sequence that you give me. So this is I'm asking, is this the central signature of a direction critical configuration under these conditions, right? So I just tell you how many points per line in the center, essentially. And I ask you, is there a direction critical configuration? As an allowable sequence, the answer is yes. If you give me the signature, I can create an allowable sequence that has that signature and it's direction critical. So I can create an allowable sequence with 2 times d1 plus d2 and so on points and n directions. but an allowable sequence. And so now we are living in this world right here. So now I'm asking, oh, what about sets of points? Now I need to see if those, and not only that, there is always one and it is unique. And so the question now is, can I actually realize it as a set of points? And the answer is no. But what was surprising to me, well, it was surprising that the answer was no, but it was even more surprising that we could actually find all of the ones that are. So the only ones that live right here, so that's this theorem right there, the only ones that are actually correspond actually to sets of points are the ones with central signature only ones, the ones that have two entries, A, B, let's say. So just two lines that pass through the center, like the exponential cross. The ones that have three entries, so three lines through the center, but two of them have only 2 points because the one tells me 1 point on one side, so there is another one on the other side. And the 2, 2, 2, 2. This is like the sporadic configuration, the only sporadic configuration for this case, the 2, 2, 2. That's it. Everything else is here. So there is a critical, and I'm talking about the criticals. There is a critical configuration for any signature. There's an allowable sequence that's critical, but not all of them are realizable. These are the only ones that are realizable. And so I told you what these are. So these four are this. So I already showed them to you essentially. The 1, 1, 1, 1, only ones, is the regular polygon. Yeah, just essentially symmetric in general position, even not only non-central. And there is 1 point in each side of the center for all the connecting lines to the center. This is the bipencil. The A, 1 is the bipencil. I only have 2 lines. I only have 2 lines in the bipencil. Goes like this. And I have all my points aligned there, almost all. And then I have 2 others like this. So that's what gives me the 1. And here I will have n minus 2 over 2. Yeah. Then I have the exponential cross. So this one right here, exponential crosses. And then I have the 8, 1, 1, which is a Tri Columnar Array. So this one, let's look at this one. So this one has 3 lines that go through the center. This one, the long one, this red one, and this purple one. So the red and the purple one are ones. So this one is a 1, the purple one is a 1, and then this long one is, in this case, it's 16 points, so this is a 6. So this is a 6, 1, 1. The sum is 8, which is n over 2. So this one over here. Oh, and let me show you the 2, 2, 2. The 2, 2, 2 is this configuration, which uses the golden ratio. So this is a 2, 2, 2 because here I have my center. I have this connecting line has 2 points. This center connecting line has 2 points on each side of the center. This one also has 2 points. This one also has 2 points. So it's a 2, 2, 2. And just to make sure that the collinearities are actual collinearities and parallelisms and everything, here are the coordinates. Here are the coordinates of that configuration. Tau is the golden ratio. And that's it. So I just wanted to end by showing you. So these are all the centrally symmetric. So this is n equals 16. These are all centrally symmetric in direction critical configurations in non-central position. for 16 points. There you have the signature, the 1111. The ones that have 2, there are three exponential crosses. This is an exponential cross. This one is an exponential cross. This one is an exponential cross, and this is a bipencil. The only difference is that in the bipencil, I don't need to have a geometric progression here. It could be any points as long as it's centrally symmetric. And this is the Tri Columnar Array. And those are, and we have them for any name. Thank you.
That's great. That's great. Thank you so much, Silvia. Let's go ahead and thank our speaker. Either use the reaction or feel free to unmute and clap yourself. Thank you for that great talk. For those of you watching on YouTube, I'm going to be going ahead and stopping the recording here. So we'll save the question period for everyone that's here in the room. If you'd like to attend for the questions, you can find the links to our website and any other future colloquium in the description below. So I'll go ahead and turn off that recording.